Hey guys, this is Unit 5, Notes number 5. Very important lesson, as with all of them, but this one in particular, as you can tell, it's the fundamental theorem of calculus, FTC, okay? Go ahead and write down your FLT here and then press play when you're ready. This is basically how everything connects, okay? So this is how we're going to bridge that gap. And you could kind of see that bridging already in the last lesson, how derivatives are related to integrals. But this is the theorem that pretty much ties it together, okay? So given a function, you're going to be able to apply either the first or second part of the fundamental theorem of calculus. And from here on forward, we'll call it FTC, okay? And there's actually two parts to it, part 1 and part 2. Now, depending on what book you're using, parts 1 and 2 are switched around. So what I want you guys to understand is don't take it too literally that FTC 1 and FTC 2 are used interchangeably, but just understand both parts of the fundamental theorem of calculus, okay? All right, here we go. So I'm actually going to give you part 2 first, because I think you should learn part 2 first before you go to part 1. But again, different authors, different approaches, okay? So here's basically what you guys have seen already. So some things to note. This, again, is called the integral, okay? So the way we read it, again, is the integral of f of x dx from a to b. So you guys understand it as the antiderivative. And, in this case, they'll use the capital F representing the antiderivative. So what happens here is you take the integral of f of x, which is some capital F of x, that's the antiderivative. And what you do here is you draw a vertical bar, and we've seen that before. That just means evaluated. Okay, from A to B. Now, these right here are called bounds. Okay, so you're finding the antiderivative specifically from one end to the other. Okay, now if your integral has bounds, we call that a definite integral. If your integral does not have bounds, you call it indefinite, okay? So when you have a definite integral, you're going to take the antiderivative, which is this right here, and then what you do naturally, okay, is you're going to evaluate it at the upper bound minus the lower bound. So what you do here is you're going to plug in your upper, minus you're going to plug in your lower. And that is your fundamental theorem of calculus part 2 in this case. Okay? So, some things to note. We mentioned that capital F represents the antiderivative. If you guys recall back in that last lesson, what did that also mean, right? We have integral, we have antiderivative, but really what are we finding here, right? We are finding the area under the curve. Okay? In this case, from A to B. And I'll show you guys that graphically in the next few problems so you have a good understanding, not just with the analytical part, but with the graphical approach as well. Okay? So here we go. Here's example 6. I had to pick and choose from different books, okay? But we can go ahead and call this example 1. Go ahead and write that down. Press play when you're ready. Okay, here. So they're asking us to find the area under the parabola, right? So naturally, if you want to find the area, that signals you to use an integral symbol. We're going to integrate our function which is x squared with respect to x. And they're telling us to go from 0 to 1, so that's going to be your bound. Okay? So you guys have to understand that when you're finding the area under a curve, they're asking you to integrate. Okay? So using the fundamental theorem of calculus, we are first going to integrate x squared. So the integral of x squared is, press play when you're ready, x cubed over 3. And then we are going to evaluate this from 0 to 1. So it's important that you know how to write it, but also know how to read it, okay? So the fundamental theorem of calculus tells us that after we integrate, or after we find the antiderivative, we plug in our upper minus our lower. So in this case, it'll be 1 cubed over 3 minus 0 cubed over 3. So we plugged in our upper, and then we plugged in our lower. Upper minus lower, okay? So here we can evaluate. This comes out to 1/3 minus 0, which is just 1/3. Now, what does that represent? That represents the area under the curve from 0 to 1. So let me illustrate that to you guys here with Desmos application, okay? So here, I believe they have the fancy symbol, but here we go. Where is it? Integral, okay? We're going from 0 to 1, and we're integrating x squared with respect to x, so dx. Check that out at the very top, okay? 0.333 is just 1/3, okay? Now, physically, if you want to see what's happening here, is we have this curve y equals x squared, and we're trying to, oh shoot, do I have the other one? I think I do. Nope. How do I not have it? Let me see. Boo, I thought I had it. You know, I think I can use, not this one, but this one here. Can I use this one? Oh, boo, I had a good illustration. I guess I can use the one that we had before. What you guys have to understand is, you know, when you're integrating, you're accumulating space. So you're kind of coloring it in from one end to the other. So assuming that that's the true area, what you guys are doing, if I can just illustrate this, hopefully it doesn't go too fast. Let me slow that down a little bit. Okay, so we'll start back at 0. What you're doing is you're finding the area under this parabola from 0 to 1. So what you're doing is you're sweeping out the area, and then you're stopping right at 1. But I can't stop at 1 because it's moving too quickly. But that's really what you guys are doing. You're accumulating space from one end to the other. So we found the area under the curve from 0 to 1, but notice how it's barred right at the x-axis. Okay, so everything is in reference to the x-axis. So 2 things here. That 1/3 came out positive. So that implies that your area is above the x-axis, okay? You have more area above the x-axis. So it gets weird because you've been taught that area has to be positive, and that still is true, but in calculus, there's a little bit more context to it. So we're going to get to that, okay? So again, first step, set it up. Find the integral or the antiderivative. You know, as we move forward, I will use the word antiderivative less and integral more, okay? After you find the integral, you plug in your upper minus your lower, which is the fundamental theorem of calculus, okay? Part 2 in this case. So here we go. Go ahead and try this one. We can call this part B. Press play whenever you're ready. So here, first thing you'd want to do is to find the antiderivative or the integral, which is x to the 4th over 4. And we will evaluate this from -2 to 1. According to the fundamental theorem of calculus, we will plug in our upper. So 1 to the 4th over 4 minus -2 to the 4th over 4. Make sure that you're using parentheses, okay? So 1 to the 4th is just 1, so that's 1/4, minus -2 to the 4th is a positive 16 divided by 4, which is 4, okay? Or you could think of this, I guess, just to make it a little bit easier, this will be 16 over 4, which is -15 over 4. Okay, what does this represent? This represents the area, okay, from -2 to 1. So about this here, okay, why is it negative and what does it mean? So let me show you guys back at Desmos here. Let me go ahead and change this to, shoot. You know what, I'll just draw it out. Hopefully I'll draw it out accurately. So from -2 to 1, the cubic function looks a little bit like this. You know what, I can do better. So something like that. And if you take a look, and I'll color it slowly here, when you accumulate from -2, which is right here, -2, all the way to 1, you're covering it with reference to the x-axis. So if you take a look here, when I color it in, up until we get about to 0. And right after 0, it's above the x-axis. Okay? And this is what you call net area. So if you take a look here, do you have more area above or below the x-axis? Okay? If you notice, there's a lot more area below the x-axis, which implies that your final answer will come out negative, which is why I have a negative answer here. Okay? So it's accumulating all that space, but again, anything below the x-axis is considered area that's below negative. Anything that's above the x-axis is considered positive above the x-axis, okay? So there you have it. All right? Notice how I'm tying in the graphical approach along with the analytical approach, right? Here's part C, something slightly different. We're finding the integral, but again, we're finding the antiderivative, aka we're finding the area under this curve from 0 to 3. Okay, so this one's a little bit different because you have multiple terms here, okay? So according to how derivatives work, integrals can be separated as well. So here, you don't have to do it, but you can if you want to. So here, this is the same thing as the integral of x cubed with respect to x from 0 to 3 minus 6, the integral of x dx. So all I did was I broke that off from 0 to 3 into two separate integrals. Notice how I still have a dx for every integral that I have. The bounds stayed the same. And this way it makes it a little bit easier to integrate. Some of you guys will be able to, actually I shouldn't say some of you guys, all of you guys will be able to integrate without having to do this step with some practice. Okay? But it will help you kind of understand the logic behind it, okay? So here, the integral of that, x cubed, is going to be x to the 4th over 4. And we evaluate that from 0 to 3. Now, don't write this part out just yet, okay? Now, over here, that 6 has nothing to do with it. The integral of x is just x squared over 2 from 0 to 3. Notice how we're still evaluating from the same bounds from 0 to 3. So wouldn't it be easier if I just wrote x to the 4th over 4 minus 6x squared over 2, all evaluated from 0 to 3? Okay, so here's what I would like for you guys to eventually do, and I know I'm erasing all of this. Here's what you do. You take a look at the yellow highlight. You integrate that guy. Okay, the integral of x cubed minus 6x is x to the 4th over 4 minus 6x squared over 2. Yes, I understand that 6 divided by 2 will give me 3, and you could definitely do that. Okay, you integrate that, but now that I have multiple terms, I have 2 terms here instead of 1. You're going to have to bracket this off, and that bracket will serve as that vertical bar to evaluate. Okay? Okay, notice how I didn't bring down the integral because I already integrated. All right? So now, this is what you guys do, and you got to be careful when you have multiple terms. What I'm going to do is I'm going to have upper, and I'll label it for you guys, minus lower. What you have to do is you have to plug in your upper wherever you see an x. And in this case, there are multiple x's here. So we have something to the 4th over 4 minus 6 times something squared over 2. And then I'm going to plug in something else to the 4th power over 4 minus 6 times something squared over 2. So here we go. We plug in our upper first. And then we plug in our lower second. Okay? Now, we just clean this up. Here we go. 3 to the 4th is 81 over 4 minus all of that. So 3 squared is 9 times 6 is 54 divided by 2 is 27. Okay? And it turns out that this comes out to 0. Now, I say it that way because it's not always the case that when you plug in 0, you get 0. Okay? It's just a coincidence. Sometimes when you plug in 0, you might have a constant left over. So just keep that in mind. So I'm just going to put 0 minus 0 here. And you know, whatever this comes out to, you could use a calculator if you want. I'll do this the old-fashioned way. I'll get common denominators. Okay, so that's going to be sidebar 81 over 4 minus, what was that, 108 over 4? I think I got that right. So if I subtract that, I should get negative, oh gosh, what is that? 27 over 4. Hopefully I got that right. Okay, and this is your answer. But don't lose context. What does that mean, right? We found the area under the curve. And there's more area below the x-axis since your answer ended up with a negative. Okay? Cool. Let's keep going. Here's part D. Try it out on your own, and then press play when you're ready. Okay, here you would integrate. So the integral of x is x squared over 2. Minus the 12 is just a coefficient, so I'm just going to bring that down. The integral of sine is negative cosine, okay? This is all evaluated from 0 to 12. Watch out for that integral. A lot of people get that mixed up, okay? Because if you take the derivative of negative cosine, you will get positive sine. So before I evaluate this, I'm going to take care of that negative there. That's really just x squared over 2 plus 12 cosine x. Okay. And then, just like before, you have an upper minus your lower. Make sure that you guys group it, because if you don't, your final answer is going to be mathematically inaccurate, okay? So here, I'm going to plug in my upper. So that's going to be 12 squared over 2. Plus 12 times the cosine of 12 minus 0 squared over 2 plus 12 times cosine of 0. Okay, so here we go. So 12 squared is 144 divided by 2, that's 72, plus whatever the cosine of 12 is on your calculator. If I hadn't mentioned it before, make sure you guys know now, whenever you guys are taking calculus, your mode should always be in radians, no matter what. Never be in degree mode. Okay, always be in radian mode. So right next to that second button on your calculator, there's a mode. Click on that. Find where radians is and then press enter so that it's bold. Okay. Every time you guys reset your calculator, second plus 712, it automatically goes into radian mode. Okay. All right, let's keep going. Minus 0 squared over 2 is just 0. And the cosine of 0 is 1. So 1 times 12 is 12. And this is what I mean, you guys. A lot of you will think, okay, I plug in 0, this whole thing is going to come out to 0. That is not always the case, all right? So you could keep going and evaluate this, but really that's not my main concern. I don't know what the answer comes out to, but I assume it's going to come out something positive, okay? Oh gosh, that's going to bug me. So you know what? I'm going to type it out. Here we go. So we have the cosine of 12. Let me make sure that I'm in the right mode here. Okay, so cosine of 12 times 12. What is going on? 12 cosine times 12. I have the old school calculator where I got to do everything backwards. Plus 72 minus the 12. So if you did it right and you rounded correctly, this should be a positive 70.126. Okay, you always round to 3 decimal places. That just means that there's more area above the x-axis because it's positive above the x-axis. Okay? There you go. All right, if none of this is making sense to you guys, please do reach out to me before you move forward, okay? All right, some properties to consider, okay? Here's property number 1. If you integrate from B to A, and now don't take the letters too literally, okay? So if your bounds were quote-unquote improper or backwards, you can easily switch it, but you have to account for a negative. So for instance, you know, normally the larger bound is at the upper, right? So what you guys normally see is something like this, the integral from 1 to 4. But occasionally, you might get the integral from 4 to 1. So what this property is stating is that you could actually just flip the bounds back to where it's quote-unquote proper, but you have to account for a negative. Okay? And I could prove that to you guys, but I really don't think it's worth your time. Yeah, it's just small beans. But if you're really curious, I can prove it to you, okay? So again, if your bounds are improper, you could always fix it, but account for a negative. All right? Okay. Here's the second property, my favorite. So remember that when you're integrating, you're accumulating space. So if your bounds are the same, you're not moving. So if you're not moving, you're not accumulating any space. So that means that your area is going to come out to 0. That's why we have, you have that many friends. That's my favorite. So make sure you guys understand the graphical end to it. If you're not moving, if you're not going from one end to the other, you're at a standstill, you're not accumulating any space, okay? And also, another way to think about it, with your delta x, if you do a minus a divided by however many subintervals, this width is 0. And it makes sense that your area is going to come out to 0 if your width is 0, okay? Anyways, here's the third one. And the third one, I'm going to have you guys look at a picture, okay? So this picture kind of shows what's happening in this equation here for the third property. The integral of f from a to c plus the integral of f from c to b is equal to the integral of f from a to b. Hopefully that made logical sense. So what they're saying is, if you're accumulating from A all the way to C, and then you accumulate from where you left off from C all the way to B, that's the same thing as going from A all the way to B. Hopefully that's logical, okay? If you start and stop and then start again where you left off, that's the same thing as, you know, going all the way through, all right? So for instance, if you start and you take 2 steps, and then you continue and then you take 1 more step and you stop, that's the same thing as taking 3 steps from the very beginning. Okay, hopefully that was logical for you, all right? So here's our last part, or the second part, or the first part, whatever you want to call it, to the fundamental theorem of calculus, okay? Before you write it, I want you to explore with me here. So this one makes a lot of sense if you approach it logically. So here we go. Let's say that there is some function called g of x, okay? The g really doesn't matter. But let's say we were integrating from some number of a function. Now, don't worry about the t. T is just a variable, what we call a dummy variable. But your upper bound is a function. And I'm going to write that in there. Your upper bound is a function, all right? So let's take a look at that integral based on our fundamental theorem of calculus, okay? So according to what we just learned, we have to take the antiderivative, which I'll call capital F of t, and then we plug in our a, and our x. Now remember, x is a function, a is a constant, okay? Now what do I do after this? I then plug in my upper, so capital F of x minus capital F of a. Keep in mind that x is a function and a is a constant, all right? Here is where it connects. Let me use a different color here. What if I were to take the derivative of g, okay? Okay, so let me highlight so you know where I'm looking. G is basically this in purple, okay? If I take the derivative of capital F of x, I'm taking the derivative of the antiderivative. I'll say that again. This right here is the antiderivative, which is why we use the capital F. So if I take the derivative of this again, I will just get little f of x. I go back to where I started, little f of x. Make sure you guys understand that before we move on. Okay? Now, capital F of a. So remember, capital F of a is a constant. This right here is a constant. And if you plug a constant into a function, you will get another constant. Now, what happens when you take the derivative of that? When you take the derivative of a constant, that goes to 0, always. So really, this is what you have, which is what we have here for our fundamental theorem of calculus. That's the logic behind it. Now, let me show you guys the glamorous shortcuts, okay? So basically, when you're taking the derivative of an integral, they cancel each other out and you end up with the function, okay? When you take the derivative of an integral, they cancel each other out. So this is how calculus connects derivatives with integrals, showing that they're inversely related, right? They're inverses. So let me show you how this works. Instead of, instead of taking the integral and then plugging in the upper and lower, and then taking the derivative of it, the shortcut here is, let me kind of erase all of the steps in between. Tell me what you guys see here. Okay, so if g is your integral and you're taking the derivative of your integral, some may notice that pretty much this just pops in here, and that is your answer. And that is your general shortcut for now. Okay? Now, all the steps in between was to show you the logic behind it. You're integrating and then you're taking the derivative, right? So here we go. I'm going to show you through many examples, and you guys are going to be experts, masters at this part because you're learning pretty much every type of variation here. So here we go. Find the derivative of the function. We'll call this example 2, part A, of the function g, where g is the integral. So the first thing you want to spot is you want to make sure that they're asking for the derivative of an integral. And this is how you know that FTC 1 applies, okay? And to be honest with you guys, I don't remember if it's part 1 or part 2, but I do remember how it works, and that's all that matters, okay? So here we go. We know that g of x is the integral of the square root of 1 plus t squared dt from 0 to x. Don't worry about the t. The t is what we call a dummy variable. It goes away eventually anyways. So here's what you do. To find the derivative, you take that upper, okay? Now first you want to make sure that your upper bound is a function and your lower bound is a constant. Those are the guidelines, okay? So because we have a constant in the lower bound and a function in the upper bound, we're allowed to do this really neat trick. And what you do is you take that guy and you replace the t. So your answer is the square root of 1 plus x squared. And that is it. Seems too easy, right? Or too good to be true, right? But it's actually just that. What you're doing is you're skipping the steps in between. Because what's the point in integrating it if you're going to have to take the derivative again? It's like going forwards to go backwards again. So let's skip those 2 steps and just call it for what it is, right? Now, there is a stipulation to this, all right? And I'll show you when we get there. So here's part A. That's where it's basic. Here's part B. Try this on your own. Press play when you're ready. Okay, so we have an integral g. They're asking us to find the derivative of the integral, okay? So we know we have to use the fundamental theorem of calculus part 1. So first let me check. Is the upper bound a function? Yes. Is the lower bound a constant? Yes. So we know we can move forward. So all we have to do, g prime of x, is we just need to take that guy and plug it into wherever we have a variable, okay? So that's going to be x squared minus 1 to the 20th power, and that's it. And again, it's that easy because we integrate and then we take the derivative. That's the same thing as undoing what you just did, right? So how does this get a little bit complex? I'll show you all the different varieties, okay? Here's part C, write it down. Okay, find the derivative of this integral here. Now, first you want to check, is the upper bound a function? Is the lower bound a constant? And in this case, it's not. It's a little bit backwards. But if you guys recall, there's that property that allows you to fix your bounds as long as you account for a negative. So here's what you do. So because it's not perfectly set up yet, I can't call this g prime of x. I can only call this g of x, okay? What I can do here is I can fix my bounds so that 50, the constant, is at the bottom, And x, the function, is the upper bound. But I have to account for a negative. All right? Everything else stays the same. So we have the cosine of t squared plus t with respect to t. Okay? Now that this is a perfect setup where the function is in the upper bound, the lower bound is a constant, I can use the fundamental theorem of calculus. So here we go. G prime of x will just be negative. And then this is where I have cosine of something squared plus something. And this is where you just plug in your x. And then really that is it. Okay, you could distribute the negative, but really that's not the main point here. Okay, so here's a case where you have to fix your bounds first in order to apply the fundamental theorem of calculus, okay? All right, so here's the next scenario for you. Now, this should be dr, not ds, okay? dr. Normally we have t's. It really doesn't matter which variable they use. They're just trying to use any variable except for x, okay? Okay, so what's different about this? Your function up here is a little bit more elaborate, right? So here's what you do. Is your upper bound a function? Yes, it is. Is your lower bound a constant? Yes, it is. So we're actually going to apply the fundamental theorem of calculus. Here we go. G prime of x equals, okay? So we're going to have sine of something to the third power. So all we do here is we'll take what we have in the upper bound and we'll plug it in. 4x plus 3. Okay? Here's what you guys have to consider. We are taking the derivative, okay? And then we inserted a function inside another function. So this is where you guys actually have to apply, I know you guys miss it, the chain rule. The derivative of what you just plugged in, the 4x plus 3, will be 4. So this is the third case that you guys are going to run into. Okay, and I'll have you guys practice that. And then there's your answer. So again, this is your chain rule. And if you really think about it, in the last few examples, the chain rule has always been applied, except the derivative of what you plugged in is really just 1. We're not looking at the x squared, we're just looking at the x that I plugged in. The x here, all right? Okay, let's try another one. Let's try this one here. Try it out on your own and then press play when you're ready. Okay, so upper bound is a function, bottom is a constant, so I'm ready for my derivative. So my derivative is really just my function squared over my function squared plus 1. I'm going to go ahead and plug in my square root of x. That just goes in there. Okay, but I also have to consider the derivative of what I plug in. So the derivative of what I plug in, and not necessarily how many times I plugged it in, but the derivative of the square root of x, also known as x to the 1/2, is 1/2 x to the negative 1/2. You do have to recall your derivatives, you guys, okay? And, you know, we could clean this up, but I would rather you guys just go ahead and keep it bare like that, okay? Okay. Here's the last, probably the most complicated that it can get, but still very easy to do, okay? Here's part F. Okay, so some things that you might notice is that the upper and lower bound are functions, right? We can only use the fundamental theorem of calculus part 1. That's a, geez, okay. FTC part 1, only when you have a function at the top and a constant at the bottom. So here's what you guys do. using that third property. So notice how I write g of x here and not g prime of x, okay? What I'm going to do here is I am going to split this integral, okay? So I'll start at tangent x, but then I'm going to stop somewhere. I'm going to stop at a constant. So I'll call this 0 because 0 is simple. You could stop at 4, you could stop at 5, it really doesn't matter. I'll stop at 0 of 1 over the square root of 2 plus t to the 4th dt. But what I'm going to do here is I'm going to continue at where I stopped, which is 0. And then I'm going to continue all the way to x squared, okay, of 1 over the square root of 2 plus t to the 4th dt. What you're doing is you're going from tangent x, you're accumulating, you're stopping somewhere, in this case it's 0, and then you're continuing at 0, and then you're moving all the way to x squared. This was that third property, okay? Now again, you could easily stop at 5, continue at 5. You could easily, stop at 4 and then continue at 4. As long as you're continuing from where you left off, you should be fine, okay? Now, why did I do that? Because now I have integrals where one of the bounds is a constant and one of the bounds is a function. This one right here, I'll highlight it in light green. That one is ready to go in regards to the derivative for FTC 1. Now, this one over here is not quite perfectly set up yet. So I know, and again, I'll call this g of x because it's not ready yet. I can easily flip these two around as long as I account for a negative. Okay, so that's 1 over the square root of 2 plus t to the 4th dt, plus the integral from 0 to x squared of 1 over the square root of 2 plus t to the 4th dt. It's a little bit of writing, you guys, but you'll get through it, okay? Now that I have a perfect setup, I have constant, function. I can go ahead and set this one up here. So here we go. Let's do this. G prime of x is equal to negative 1 over the square root of 2 plus, in this case, I'm going to plug in tangent. Try to squeeze that in there. Tangent x. Okay. But I also have to consider the chain rule. The derivative of tangent x is secant squared x. Over here, plus, this is just going to be 1 over the square root of 2 plus, in this case, I'm using x squared to the 4th. And the derivative of what I plugged in is just 2x. Okay? And although that's super messy, that's enough for you guys to leave it as is. Okay? That's as tough as it gets. Okay? You've covered pretty much every situation. If you don't have a constant in the bottom and a function at the top, you could always switch your bounds if you need to, just account for the negative. If you have two functions, you could split it down the middle somewhere at 0 or at 5 or wherever. So that's how you would apply those properties, okay? Okay, so rapid fire questions. Here we go. You don't have to write it down. You just have to answer it. These were some AP released questions. I kid you not, okay? AP released questions. So questions that you would see on the AP exam. Now here, some things that you might not have seen in this lesson, but d over dx is just the derivative. So they're really asking us, well, what's the derivative of this integral? Okay, try that on your own. Press play when you're ready. Okay, the derivative of this, it's a perfect setup for the fundamental theorem of calculus part 1. So you just take that upper bound and you plug it into the x there, right? And you end up with C. Boom. It's that easy. All right? Okay. Let's do this one here. Press play when you're ready. Okay, we're taking the derivative of an integral. We're plugging in x here. So that's the cosine of 2 pi x. Which one is that? Oh, yeah, there we go. Right there. Boom. And then you're done. Okay? All right. Written a little bit differently. If f of x equals that integral, then f prime of 2 equals. Okay? You could try this on your own. Press play when you're ready. So the trick here is to first find f prime of x. And that's the FTC one there. We're taking the derivative of an integral. That should come out to the square root of x cubed plus 1. And now that I know that, f prime of 2, which is what they're asking for, right, is just going to be 2 cubed plus 1. That's just going to be 3. Boom. Okay? Very doable, you guys. And if I haven't told you guys before, this AP exam, people put this AP exam like on a pedestal, like it's unattainable. This AP exam is very easy to do, okay? I want you guys to understand how easy it is with work, obviously, but anybody can pass this exam, okay? Just with a little bit of practice. So, here's one. Try this one here. Press play when you're ready. Okay, so your f is an integral. They're asking for f prime, so this is FTC1. So we take x squared and we plug it in here. So that's going to be the square root of 1 plus x squared cubed. But we also have to consider the derivative of what we plugged in, which is going to be 2x. So if you clean that up, you should get 2x square root of 1 plus x to the 6, which is a. Okay? That's it. Yeah, that's it for today. Okay. So again, just to revisit, FTC2 is really just integrating definite integrals. So f of x dx from a to b, that's really just capital F of b minus f of a. You guys are used to that, okay? FTC1 is taking the derivative of an integral. And I showed you all of those really neat tricks to kind of get past the problem there, okay? And that's it. So practice as much as you guys can, okay?